Let's try the same thing for cosine of x at a equal pi. So again, I want you to write the original function down and then make your list of derivatives. So negative sine, negative cosine. So this turns into positive sine, and the fourth derivative turns into cosine. And you're kind of expecting that. You remember that the four derivatives with sine and cosine, whoops, gives you, oh shucks, how did that happen? All right, there. Okay, so here we go. The four derivatives wraps us back around to the original problem. This should be an equal sign. There we go. Okay, so now we're going to make the list plugging in pi. So cosine of pi, you know, is -1. F prime of pi, you know, is 0. So the second derivative at pi will give you a +1. Sine of pi again is 0. Then the fourth derivative at pi will give you a -1. Okay, so let's put it together. So our function is, so you start with f of pi, so it'll be -1 plus f prime of pi, 0, x minus pi over 1 factorial. I'm just going to put these 0 terms in for effect in the beginning, and then I'll erase them. Plus, so now I'm moving on to the second derivative, which is 1, x minus pi squared over 2 factorial, plus 0, x minus pi cubed over 3 factorial, plus a -1, x minus pi to the 4th over 4 factorial. And it goes on forever. Okay, so let's simplify and take away the 0 terms. So I have -1, this is gone. Then I'll have plus 1 over 2 factorial, 1 minus 1 times x minus pi squared, plus, this term is gone. Then I have, so let me erase the plus because it's going to turn into negative x minus pi to the 4th power over 4 factorial, dot, 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 dot. Okay, so now I get to put together the pattern. So the pattern, remember, I want to start at n equals 0, and when I plug in n equals 0, I want it to generate this term. When I plug in n equal 1, I want it to generate this term, and n equal 2. So I notice that they're going to be even numbered terms, right? So 2, 4, and it looks like it starts at like 0. So generating even terms, I'm going to want to use the expression 2n. And while I'm talking about it, to do odd terms, you want to use 2n plus 1. 2n minus 1 can work, but I want you to use 2n plus 1 when you're making up these Taylor series. It'll work better for you. All right, so let's look at, say, this term right here. Remember, the 0th term isn't that useful to look at. So it looks like I've got a 4 factorial on the bottom, and I've got an x minus pi to the 4th, and I've got, looks like a changing sign. So let's deal with the easy thing first. So I've got a 4 factorial in the denominator. So when I plug in 2, I want to get a 4 factorial. So I want to make it a 2n factorial. These parentheses are a really big deal, because if I plug in n equal 2, that gives me a 4 factorial. If I plug in n equal 1, that gives me a 2 factorial. All right, so then I've got a factor of x minus pi to the 2n, because again, when I plug in 2, I want to get 4. When I plug in n equal 1, I want to get 2. N equals 0, that gives me a 0 power for that. So now I got to worry about taking into account this negative sign. So this changes from negative to positive to negative. So there are two options. So what I'm going to suggest, if it looks like it's changing sign, that you start with trying this. If that doesn't work, then this one will. So let's look at this. If I try plugging in -1 to the n, what happens when I plug in n equals 0? If I plug in n equals 0, -1 to the 0 gives me a positive. Oh, that's not going to work. So let's change it to n plus 1. Now if I plug in n equals 0, I get -1 to the 1 power. That's negative. Let's make sure it works for n equal 1. If I plug in n equal 1, I get -1 squared. That's positive. That works. N equal 2. -1 to the 3rd power, that's negative, that works. So one or the other will work if it's changing sign.